The main theorem of this section is if you have a sequence of differentiable functions on a closed interval, and the derivatives converge uniformly, that's supposed to say uniformly to some g, if there's any point such that f of x naught as a sequence converges, that means that the original sequence of functions has to converge to f, and f prime equals g, which is what you'd hope for. That is, the derivatives converge to f prime, whatever that does. I'm going to give you an example and a non-example, and I'm going to prove them. So the example is I'm going to let my f sub n equal 1 over 2n times x squared. Okay, so that's what we're going to go with. Oh, and then I have to give you an interval on, how about 0, 1 closed. So that's the example. So what I'm going to do, this is definitely, all these are differentiable. The derivative is 1 over n times x. And I need to prove that this converges uniformly. I'm also going to need to prove that there's a point in here such that f of x naught converges. And then I will also prove that fn goes to f with f prime equal to g, although you wouldn't have to using this theorem because that's what the theorem gives you for free. So I'm going to prove that fn prime converges uniformly to 0, where of course 0 is the 0 function, remember. Like so. In other words, I need to prove that the derivative here, which is x over n, right, drop the multiply by 2, subtract 1 from the exponent, converges uniformly to 0. And how do I do that? Well, I can do that by, first of all, let epsilon be bigger than 0. So then there is an capital N such that 1 over n is less than epsilon by the Archimedean principle, and then for all n bigger than or equal to n, I get fn prime minus my limiting function is 0, so that's really my g, that's the g in this, is equal to, and notice this is not going to rely on x. This is going to equal x over n minus 0, which equals x over n. Now remember, I'm just on the interval 0, 1. So the biggest this could possibly be is 1 over n. I could replace the x with the biggest thing it could possibly be, and that's less than or equal to 1 over capital N, which is less than epsilon. So give me an epsilon. I'm just going to find this capital N that works for every single value of x. So I've proved that this converges uniformly. Now the only thing left to prove for this example, well, the only thing I need to prove for the theorem is that there exists an x naught. So I'm going to let x naught equal to 0. Then I'm going to prove that converges. F of x naught sub n equals fn of 0, which equals 0 squared over 2n, which equals 0, which converges to 0, and you won't be surprised to learn that converges uniformly since 0 is the only thing there. So when you're using this theorem, you basically just need to prove these two things, and then you will know that fn converges to f for some f with f prime equal to g. Okay, but let's prove that just for fun. So I could prove this directly by, let epsilon be bigger than 0, and then there exists an n belonging to the natural numbers such that 1 over n is less than 2 epsilon. And then for all n bigger than or equal to capital N, right, I'm proving that this thing converges uniformly to a function on 0, 1. I'm going to prove it converges to 0. F sub n of x minus 0 equals f sub n of x equals x squared over 2n. Remember, we're just looking at the interval 0, 1, so this is going to be less than or equal to 1 squared over 2n equals 1 half, 1 over n, less than or equal to 1 half times 1 over capital N, which is less than 1 over half. I'm going to stop right here because my pen broke.